Hello students and YouTube learners. This is Dr. Satish Singhal, PhD, Professor of Computer Science, El Camino College, Torrance, California. Now I'm here for the searching and sorting video 3, and in this video I'll do part of the binary search, basically the principles and the algorithm, and in the next part, which will be pretty short, I'm going to do a demo of the source code for an array. So let's look at the principles of binary search. So, slowness of linear search. We discussed linear search in video number 1 and 2. Linear search can work well if array is not too large. Of course, understanding too large is kind of a relative term. And in computer science, we evaluate an algorithm for the worst possible performance. That's one of the evaluations. There are other evaluations done as well. And such analysis is called a big O analysis. You will learn a lot about big O analysis in data structure class. The worst search performance in linear search is proportional to the size of the array being searched. So if array is like 100,000, 200,000 or something, probably you can manage quite well with the linear search. But let's say array became 30 million, 40 million, then the performance being proportional to 30 or 40 million degrades quite a bit. So in large arrays, linear search would be inefficient. So what is the first search technology? It's a binary search. A search technology called binary search is faster for searching large arrays. That is needed because very often businesses need to search through huge volumes of data, which are called data warehouses. One prerequisite for binary search, however, is that the array must be sorted. Sorting can be done in ascending or descending order, but sorting in ascending order is the norm. Understand that a sorted array will become like your good old dictionary, in which all words are arranged in ascending order alphabetically. So taking an example of dictionary, we're going to explain theory of binary search. Imagine that you needed to look up word care in a dictionary and its meaning. Then you open the dictionary somewhere in the middle, and middle letter is M. So dictionary will have words starting A to M in this half and N to Z in this half. Since I'm looking word for care is less than M, so immediately I can discard this half and search only in this one. Okay, so I said that already. C in care is less than M, so all of a sudden I discard half the dictionary, M to Z, and now I split that one into two portions. So first will be, so let's go back for a second. So I have to look in this half, but obviously C is not M either, so I can discard M also. So that means in this half I need to look up only between A to L. Okay, so if I split A to L in the middle, one portion will be A to F, this portion, other portion will be G to L. Okay, and you can see that care started with C and it is less than F. So not only I can discard G to L, I can also discard F, and next time I'm going to be looking only in the portion of A to E, which I split in the middle will be A to E, in the middle will be A to C and then D to E. So then I have landed in the portion that has the words with C. Now of course I'm not assuming that there will be just one page with words of C. There could be many. So I may have to split those two. But we have reached the letter C. We may need to do splitting of pages with C. But with few more splits, we'll find the word care. So that's the principle behind binary search. You can actually take if you have one lying around, a very old phone book, white pages where there are alphabetical names, and you can actually do this experiment yourself. Pick a name and split the phone book in the half, and then another half, and you will find it. Okay. A computer obviously does it better than we humans do it by hand. So that's the principle. So this is the basic principle of binary search, is to successively reduce the search domain by half each time. In this case, worst search time is proportional to log to the base 2n. This is not log based 10, log to the base 2, where n is the size of the array. And you remember that worst search time, or big O of linear search, was proportional to n, size of the array. So if I improve that to log to n, that is an order of magnitude lower than big O of n. So binary search is indeed a very fast searching technology. Of course, you require the array to be sorted, and in current day there are some very fast sorting algorithms that accomplish sorting also very fast. So combination of fast sorting and binary search works out quite well. Okay. So if you want to apply now, we showed the binary search principle through the dictionary. Now we want to apply binary search to the sorted array searching. Imagine I need to search for a key in the array, then I could designate 3 points in the array. A low point, which will be starting point or starting index of the current search area in the array. Now, if you want to consider a whole array, then that should be 0. But you can also always search portion of an array if you like, but otherwise it will be 0. And the high end point or ending index of the current search area in the array. So that will be simply your logical length minus 1. And if array is filled to the capacity, that will be capacity minus 1. And then there is a mid index, exactly middle index of the current search area. So how do we find this mid? We take low plus high divided by 2. And that's an integer division. Don't forget that. It's not going to give you a floating point value. You can't have array index of 10.5. So please don't make that mistake. Okay. Array index can only be an integral value. So if you take 10 plus 0 plus, let's say high index was 11, so 0 plus 11 is 11, divided by 2 will not be 5.5, it will be actually 5. Integer division, don't forget that. Okay, so now I'm going to show you a slide with an array which is sorted, and I'm looking for a number in that. And first I'm just going to show you schematically, and then I'm going to show you the algorithm and walk the algorithm through that picture. So imagine this is the array, sorted array 1 to 10, and I'm looking for number 7 in this. So my low is 1, high is 10, so my midpoint is low plus high divided by 2. So that will be 11 by 2. 11 by 2 is 5. No, I'm sorry. High index is 9. My mistake. These numbers are kind of confusing me a little bit. So high index is 9, low index is 0. 0 plus 9 is 9, divided by 2 is 4. So my midpoint is index of 4. So now you can see that value here is 5 and mid index 7 is actually greater than 5. So I can reject the mid index value as well as everything before that. So I've discarded this much array, and then my low index becomes here at the index 5 or the value 6, and high index doesn't change so far. So now I have index of 5 and index of 9. So I sum them up. 9 plus 5 is 14. Divided by 2 will be 7. So I land here. That's my middle index. And I compare key 7 with the value in the middle index. That's easily done. Now you can see 7 is less than 8. So it's not going to be in this part of the array. It's going to be before that. So I reject not only this but rest of it, and then I land with 6 and 7. So here index is 5 and 6. 5 plus 6 is 11. Divide by 2. 11 by 2 is 10. Sorry, 5. So my midpoint is 5 this time. And then I see that 7 is greater than 6, so it can be this. So no need to split now. It can, if there are only two elements, it can only be this, and that means I found it actually. Okay. So that's how the binary search works. Okay, let's take the algorithm, and I'm gonna come out of this, or maybe I don't need to. This is my algorithm, which I'll convert in the next video into the source code. I set a Boolean flag found to false, and imagine that binary search function which I'm using gets the array itself. Name of the array is array. Might be a little confusing. And length is the logical length of the array, and key is the argument that I'm looking for. I'm looking for the key, like 7 was the key in the previous video. Okay, so maybe I'm better off doing it this way because I can go back and forth like this. So if you go back here, my high index was 9, low index was 0. So length was actually 10. So this is 9. Okay. Then my loop condition is while high index is greater than or equal to low index. Remember, at the end you'll be left only with 1. So then high index and low index will become 1. That's when you actually find it. So two loop conditions, while high index is greater than or equal to low index, which is totally logical right now because this is 9. Low index is 0. So that's totally fine. True. I set the found to false. Not found will be true. So first I do is I find the mid index, just I explained before. So in this picture, low index was 0, high index was 9. 9 divided by 2 would be 4. Okay, so we get the 4. So there are 3 if statements here. If mid index equals key, then I set the found to true. Not found will be false. I'll exit the loop. But of course, in this case, as you know, mid index is actually 5. Value at the mid index is 5, but key we are looking for is 7. So this doesn't apply because I didn't find it. Mid index value is 5. Value I'm looking for is 7. So this doesn't apply. Mid index value is 5. Value I'm looking for is 7. So that's the case that applies actually. So what I do is I move the low index to mid index plus 1, mid index was 4, so I actually go to 5. So that becomes the new low. Excuse me. And you can see that my high index is 9, low index is 5. So this loop condition is still true, and of course value found has not been updated, so this is still true. So I enter the loop again. So I compute the new mid index, which will be 5 plus 9 is 14, divided by 2 will be 7. That's my new mid index now. So once again, value here is 8, key I'm looking for is 7. So 7 and 8 are not same, so this will not apply. And value at the mid index is 8, key I'm looking for is 7. So this does apply right here, because this is 8, this is 7. So I will set the high index to mid index minus 1. So I'll set the high index to be here, and that's how we get here actually. Okay, so that's not my new sub array I'm searching for. So low index is 7, high index is, low index is 5, high index is 6. 6 greater than 5 is true, and found was still false. So I enter the loop again, and this time I compute the new mid index, which is low plus high divided by 2. So low was 5, high was 6. 11 divided by 2 is 5. Wait a minute. 11 divided by 2 will be 5. Yeah, 5. Okay, no problem. So value at 5 is what? Value at 5 is 6. So this case doesn't apply. And value at index 5 was 6. That didn't apply. So only left is that case that will apply will be this one. Okay, array mid index is 6, key I'm looking for is 7, so it's lower actually. So it'll be this case here, and in that case I set the low index to index plus 1, and my mid index was 5, so I set it to 6. And when that happens, my loop condition is that high index and low index are same. Okay, so this is true, not found is true, and this time I found the key and array mid index, which was set to here. I found it, and I found the key basically. So how many split it took me to find it in this array? 1, 2, 3, 4. Just in 4 splits I found it actually. Okay. Now if you did the linear search, you will know. Of course this is sorted, so it's not the same situation as random. But if it was not sorted, it could have been here, it could have been there, it could have been exactly at the location. But the worst performance would have been like it's here or it's not there. So worst performance would be proportional to size of the array, like 10. But in this case, notice, that means we would have to do at least 10 iterations. But in this case, we just found it like in 4. 1, 2, 3. Just in 4 iterations we found it. So this is an incredibly fast performance in the binary search compared to the linear search, even for such small array. In fact, as arrays get smaller and smaller, the difference between the two disappears. It becomes smaller and smaller, actually, performance difference. So we gave you a example of a dictionary, then of an array, and then we discussed the algorithm. In next video, which will be last on the searching, I would do the code, take this algorithm, convert that into a code, have a array in the main function, pass that to this function, and just walk you through for the search in that case. So you will see the code. That will be a pretty short video. But if you understood this principle, you probably understand most of it. Alright, so that was binary search. This is Dr. Satish Singhal, PhD, saying thank you for watching this video, and I'm going to see you in next video, source code for binary search, and then I have a couple of more video in this chapter on sorting, and we'll complete that in that case.